A single liter of gasoline contains the same amount of energy needed to power the average home for 6 hours. The simple concept of extracting and utilizing this cheap, dense store of energy has fundamentally shaped how our society has evolved over the last century. And deep within the gasoline internal combustion engine, initiating every single combustion event that converts this stored energy into powerful motion, is the deceptively simple spark plug. The first documented use of a spark plug in an internal combustion engine was attributed to the Belgian engineer Jean-Joseph Etienne Lenoir in 1859. Lenoir is known for developing the first internal combustion engine, which burned a mixture of coal gas and air. His engine operated crudely with no compression phase. The air-fuel mixture it aspirated was ignited by a jumping spark ignition system, which he patented in 1860. Lenoir's ignition system created sparks by using high-voltage electricity to jump an air gap. This was accomplished by sending mechanically generated low-voltage pulses through a type of electrical transformer known as a Ruhmkorff coil, an archaic form of the modern ignition coil. The coil would transform the low-voltage pulses into lower current, high-voltage pulses suitable for spark generation. The underlying concepts that Lenoir's ignition system operated on can still be found within the ignition systems of modern vehicles. By the turn of the century, refinements to the basic design of a spark plug would result in patents being filed by Nikola Tesla, Frederick Richard Sims, and Robert Bosch, all around the same year. Robert Bosch would become the first company to develop a commercially viable spark plug designed to be paired with a high-voltage magneto-based ignition system. Other notable contributors to improvement of spark plug manufacturing came from the Lodge brothers, who founded Lodge Plugs Ltd., Callum Lee Guinness of the Guinness Brewing family, who developed the KLG brand, and Albert Champion, founder of the Champion Ignition Company. To this day, his name survives as both the Champion spark plug brand and as the AC in GM's AC Delco products brand. Though spark plugs may appear as simple devices, reliably igniting over 20 million combustion cycles while surviving exposure to the extreme temperatures and pressures of ignited fuel would prove to be a formidable challenge. All spark plugs are fundamentally composed of two electrodes separated by an insulator. These electrodes converge at a spark gap where spark generation occurs. As the initial current flows from the ignition coil to the spark plug's electrodes, the flow of electricity is initially blocked by the insulating properties of the air-fuel mixture within the gap. As the voltage pulse ramps up, the potential created between the electrodes begin to restructure the gases within the spark gap. As the voltage increases further, the insulating limit or the dielectric strength of the spark gap gases begin to break down, causing it to ionize. Because ionized gases are conductive, current begins to flow between the electrodes, rushing across the spark gap. This rapid surge of electron flow quickly heats up the gases within the spark gap to over 50,000 degrees Celsius, causing a subsequent rapid expansion of the ionized gas. This rapidly evolving heat and pressure wave causes the gases around the spark gap to ignite and burn on their own, forming a small fireball known as a kernel. The kernel flame front progressively ignites the rest of the air-fuel mixture in a highly controlled pattern, creating high-pressure gases in the process. Though the voltage required to trigger a spark event can be as low as 15,000 volts, voltages between 50,000 and 100,000 volts are common in modern automotive use. Higher voltages allow more energetic ignition events by creating sparks that are larger, hotter, and longer lasting. The first spark plugs used in early low-speed, low-compression gasoline engines had a very minimal set of operational requirements. Their main design concern were the plug's fit and position and its ability to maintain an operating temperature range that would allow the plug end to self-clean by burning off deposits. This operating temperature refers to the actual temperature at the spark plug's end within the running engine. This temperature can range from 500 to 1,000 degrees Celsius, and it's primarily determined by the temperature within the combustion chamber and the thermal conductive properties of the spark plug's design. The thermal properties of a spark plug are designated by a relative heat range. A hotter plug, for example, is designed to be a better thermal insulator, keeping more heat at the end of the plug, while a colder plug conducts more heat away from the end, lowering its operating temperature. It should be noted that a spark plug's heat range has negligible effect on the actual combustion chamber temperature within the cylinder. It more so represents how the plug responds thermally to its environment. For example, peak engine torque produces the highest combustion chamber temperatures while idling the least. With older spark plugs, a specific heat range had to be chosen to match the intended type of driving the engine would experience, with the ideal operating temperature of the plug. Early spark plugs used a stack of minerals such as mica or porcelain as an insulator, which was compressed and held in place by a nickel-chromium electrode and housed in a multi-piece assembly. Because achieving operating temperatures that promote self-cleaning was the primary concern, these plugs operated at a very narrow temperature range and degraded rapidly due to limitations of the materials used and the electrode's construction. It was common for these early plugs to have lifespans of just 960 kilometers or about 600 miles. As engines began to produce more power, the demands on existing spark plugs started to increase. The emergence of leaded gasoline in the 1930s would also cause aggressive deposit buildup on the mineral insulator ends. To keep up with this, construction was shifted towards a single-piece design composed of a ceramic called sintered alumina. Pioneered by both Siemens and the Champion Ignition Company in the 1930s, sintered alumina had almost the same thermal expansion as the metal parts within the spark plug, along with 3 times the strength and electrical insulating properties when compared to mineral insulators. It was also a good conductor of heat while simultaneously being able to withstand high temperatures, and it could be manufactured at low cost and with high mechanical reliability. Sintered alumina plugs operated at much higher temperatures, which helped counteract the fouling issues caused by leaded fuels via deposit burn-off. Its electrical insulation properties also allowed much higher voltages to be used, tolerating up to 60,000 volts. This would be further improved by the addition of ribs, which increased the surface area of the insulator, further improving electrical insulation and resistance to dirt and moisture. Some of these plugs also started to incorporate a ceramic series resistor in order to reduce radio frequency noise created by spark generation. This feature became more important as electronics started to migrate into vehicles. The next big change in spark plug design would occur during the 1970s as a direct result of policy changes. In 1974, the US government began to impose fuel mandates and stricter emissions regulations, which prompted the removal of lead from gasoline, the introduction of catalytic converters, and the move to smaller, more efficient engine designs. Existing spark plugs struggled with these new requirements, forcing a major redesign. The factors that drove these new designs shifted to broadening a plug's heat range and making them more consistent in performance in order to prevent damage to catalytic converters. By removing lead from fuel, the temperature required to burn off deposits increased. This created a problem at lower engine loads where combustion chamber temperatures are lower. Using a hotter plug can combat this, but it also introduces the problem of overheating at high engine loads. Furthermore, lead-free gasoline suffers from a higher likelihood of pre-ignition. Pre-ignition is a condition in which the air-fuel mixture ignites before the spark plug fires, potentially causing severe engine damage. Using a hotter plug can further exacerbate this risk. The solution to this dilemma was to redesign spark plugs so that they self-cleaned at lower temperatures, yet still function reliably at higher engine loads. This was accomplished by changing the center electrode material to a copper core, as well as refining its shape. Because the central electrode is designed to eject electrons in a spark event, it's designed to be the hottest surface on the spark plug. This makes it easier for electrons to be emitted, promoting localized spark formation. The electrical discharge brought on by the ionization of gases within the spark gap is known as a corona discharge, and it typically forms where the electric field strength is largest within the electrode. This tends to be where the radius of a curved surface is the smallest, such as an edge or at a sharp point. Though a sharp point would erode far too quickly for practical use, the end of copper core electrodes are designed with a sharp edge that erodes in a consistent manner. As the plug wears, the edge will slowly begin to round over, reducing the strength of the spark it produces. The service life of a copper core spark plug can be extended by periodically cleaning and refiling the end back to a sharp edge. Copper core spark plugs can easily achieve a service life of around 32,000 kilometers or about 20,000 miles. Over the next 20 years, other configurations of spark plug designs would be explored. One common variant is the multiple ground electrode plug. This configuration extended a spark plug's service life by providing multiple ground paths for a spark to form across. This allowed spark formation to move from an eroded edge to a sharper one on the center electrode, though at the cost of potentially obstructing flame front development. Another significant configuration is known as the surface discharging spark plug. These plugs are designed for engines that physically cannot accommodate the tip protrusion of a traditional spark plug. A notable example of this is the face-sweeping action of the Wankel engine. Surface discharging spark plugs have a recessed, stubby center electrode that forms a spark gap to the plug's body, presenting a predominantly flat ignition face. By the 1990s, engines began to grow more sophisticated and powerful. Computer-controlled ignition systems were becoming common, and the need for more energetic spark generation with newer high-compression and force-induced engines was becoming apparent. This was accomplished by moving ignition coils into assemblies that sat directly above the spark plug. Known as coil-on-plug ignition, the one coil per cylinder configuration, coupled with the shorter direct path of current flow, allowed for extremely high voltages to be used, often well past 100,000 volts. The higher voltage allowed for significantly larger spark gaps, creating energetic sparks that promote a strong, clean burn within the combustion chamber. Around this time period, the development of noble metal high-temperature electrode spark plugs were becoming commercially viable. Composed of center electrodes made of a thin wire of metals such as iridium, tungsten, or platinum, these class of spark plugs offer fine, extremely sharp-edged electrode ends that had high melting points and were far more durable than copper cord spark plugs. The inherent durability of noble metal spark plugs made them an ideal match for newer, higher voltage ignition systems, requiring no regular service and offering a remarkable service life of over 160,000 kilometers or about 100,000 miles. It was not possible to operate a vehicle for years without any service to the ignition system. On modern fuel-injected cars, higher compression ratios as well as tighter control of combustion timing is used to extract as much energy as possible, increasing power and efficiency. As an engine's rotating speed increases, triggering an ignition event slightly before the point of maximum compression within a cylinder or advancing timing is done to give the combustion process more time to occur. Changes to the air-fuel mixture are also made to accommodate for load and speed changes. Under certain conditions, uncontrolled combustion can be triggered as small packets of air-fuel mixture explode outside of the envelope of the normal spark plug triggered combustion front. This is known as detonation, and it can occur when timing is advanced too aggressively or the air-fuel trim is mismatched for the conditions within the cylinder. Though this can be mitigated by using a higher octane fuel, which lowers gasoline's volatility, the engine control unit is generally tasked with finding a balance point between preventing detonation and achieving ideal combustion timing. In order to accomplish this, detonation or engine knocking needed to be determined so that ignition timing and fuel trim can be tuned accordingly. Engine knock sensors were developed for this task, and they functioned as highly tuned microphones, listening for the tones of sound produced on an engine block as it experiences detonation. Though the technique is simple, its inherent inaccuracy and slow response rate limited how granularly ignition and mixture adjustments can be made. The ability to accurately manage detonation also kept combustion chamber designs relatively conservative. During the late 1990s, several manufacturers were researching better methods to detect detonation. The focus of this research primarily led to moving sensing from outside of the engine to directly measuring each combustion event within a cylinder. And the sensor that would drive the system was an inexpensive, easily serviceable part that sits directly in the combustion process, the spark plug. Because burning air-fuel mixture becomes ionized and conductive immediately after a spark event, it becomes possible to repurpose the electrodes of a spark plug to measure the conductivity of the gases as they combust. By sending a low-voltage current through the spark plug's electrodes, the chamber ionization can be sampled. Between spark events, the ionization curve can be measured and compared to a known clean burn set of data, allowing perfect direct detonation detection. Misfires can also be easily detected by sensing the lack of ionization. By the late 1990s, the processor within engine control units became powerful enough to perform the needed digital signal processing for ionic sensing knock detection. Commercial implementations of the technology started to appear, with Saab and their Trionic engine management system being one of the first ion sensing ignition systems on a production car. With the ability to directly detect detonation at each cylinder and at each combustion event, unprecedented levels of engine control now become possible, pushing forward more aggressive designs. As ionic sensing systems became more sophisticated throughout the 2010s, this method now allowed spark plugs to provide individual cylinder information to the engine control unit on fuel trim and peak cylinder pressure position. This level of information now allowed engine control units to rapidly tune in each cylinder, improving overall engine efficiency as well as offering a new diagnostic tool for engine service. With it already peaking in performance and reliability, the evolution of the spark plug will likely soon reach its end within the coming decades as battery technology improves and the automotive industry as well as the market further embraces electric vehicles. Interestingly, it was electricity that first pioneered the emergence of the internal combustion engine, and it will likely be electricity that ushers in its end.